Professor Laura Greene from Florida State University, and also she's at the U.S. National High Magnetic Field Laboratory. So Laura studied physics at the Ohio State University and obtained her PhD in experimental condensed matter physics in 1988 at Cornell. And she was telling us a little bit about that yesterday. She then went to the Bell Labs and Bell Core in New Jersey. And in 1992, she started her professorship till 2015 at the University of Illinois at Urbana-Champaign. And since 2015, she's the Francis Epps Professor of Physics at Florida State University in Tallahassee. And she is the chief scientist of the National High Magnetic Field Laboratory, which encloses 3 universities. So in fact, the State University of Florida, the University of Florida, and the Los Alamos National Lab. So this is really a very, very, very big job that Laura is doing for the research. So in fact, her research interests are strongly correlated to electron systems. So she's an experimentalist by, I would say, by nature, because she's very passionate in developing new methods of probing, for instance, properties like unconventional superconductivity, what we call heavy fermions, topological insulators. So all type of new quantum materials where you have, in fact, phases or properties that are a consequence of the interaction between the electrons. So for her work, which is outstanding, she has received many awards and honors. And just let me mention a couple of them. So she is Fellow of the American Academy of Arts and Sciences. She's a member of the National Academy of Science since 2006. She's a Fellow of the American Physical Society. She received the Maria Goeppert-Mayer Award of the American Physical Society in 1994. In 2017, she was the president of the American Physical Society. She's a member of the President's Council of Advisors on Science and Technology. She received last year the Tallahassee Scientific Society Gold Medal Award, and many others that if I continue, Laura, you are not going to start. So it's a pleasure for us that you are here today, that you had this piece of time also to tell us a little bit about your research and your life. And the title of your talk is Dark Energy of Quantum Materials. So we are looking forward to your talk.
Thank you, Rosa. That was a really sweet introduction. I'm a little floored. Thank you. And you got the physics right. So this is the last talk. I'm going to make it fun. I think about education, outreach, and public engagement. This will be more of a public engagement thing. And I hope you enjoy it. Let me go to the next slide. I call it the dark energy of quantum material. Let's see, let me get rid of this thing. I don't think I can. Okay. I call the talk the dark energy of quantum materials because it's sort of my view of 35. It's a very broad view of what we call quantum materials. And it also shows the connectivity across many areas of physics. And we like to ride the dark energy wave because it's so fun. And one thing I want to get across is there's many, many unsolved problems that are no less fundamental than those in cosmology, like gravity waves, dark energy, and dark matter. And I just want to say that I'm making analogies, and the analogies are fun. They're not really meant to be all that serious. So it's to give you a bit of wonder. And I'm comparing things that go across the universe and things that are down to 10 to the minus 10 meters. What this little picture of here is a cartoon of what we call electron nematicity, when the electrons, for reasons we don't completely understand, form little cigars or sausages, whatever your favorite poison is. And we don't know why the electrons form those clumps. So I'm making comparisons at 10 to the 36 in length and 10 to the 70th in power. So first I'm going to talk about, can I get rid of this thing? I don't think so. There we go. I'm going to tell you, most of my talk will be about the National High Magnetic Field Laboratory. And then I'll tell you a little bit about superconductivity and the fun analogy. And I love this little picture, caution analogies ahead. So if you do quantum materials, you can't really taste or feel a de Broglie wavelength, but we know they exist because we make analogies. We think about swimming around in lattices, but we don't know if we're right or wrong unless we have a systematic way of doing it. And the analogies help us create experiments. We can prove ourselves wrong or right. And in the lower right here, I have a picture of the Bohr model of the atom. We all love it. We teach it. It helps us understand quantum mechanics. And if you push it too far, it's wrong. So, okay, no, I'm not, this always happens, there we go. So the National High Magnetic Field Laboratory has this mission, and it hasn't changed in more than 2 decades. The mission is to operate a world-leading user program. We're primarily a user facility, and we have to also carry out some great in-house research in support of that user program that helps bring interesting users in from all over the world. We're constantly on our mission developing new magnets and new instrumentation, new probes. And what's interesting about being an NSF funded, our core funding comes from NSF, is that unlike most of the other US national laboratories, we have as a major charge of education and outreach. And I recommend going on the website and seeing Magnet Academy and things like that. I'll mention a couple things at the end. So the national, as Rosa said, the National High Magnetic Field Laboratory is in 3 locations. The main campus is in Florida State University in Tallahassee, which was in the news yesterday with all the hurricanes coming around. And it's a very large facility. I recommend coming to visit. If I walk from my office to my laboratory, my Apple Watch says good steps. And it's the home of the largest DC field in the world, the 45 Tesla hybrid. It's DC, so it's a continuous wave magnet. 45 Tesla is the largest in the world. Now, that's about 100,000 times the Earth's magnetic field, or about 50,000 times a refrigerator magnet. So it's a high magnetic field. We also have things like we can do NMR at 21 Tesla, and there's several other. I'll mention some other facilities. At the University of Florida, I'll just say also at Florida State, we have 4 user facilities. You won't remember them. I'll mention some of them with examples. And 2 laboratories, our Applied Superconductivity Laboratory and our Magnet Science and Technology, where we design magnets. And I'll mention those a little bit as examples. At University of Florida in Gainesville, we have 2 user facilities. We have something called the high B over T facility. The fields aren't as high, but it's the highest ratio of B over T in the world. And there's some substantial experiments that can be done there. And one I'll give you several examples of is Advanced Magnetic Resonance Imaging and Spectroscopy, AMORIS facility, where we do MRI up to 21 Tesla. At Los Alamos, where I'll be going Sunday, we have our pulse field facility, which we can go up to 101 Tesla of pulse magnets that go for milliseconds. Now, here's a picture of the rotor. I have a long history with this rotor because it was used for inertial confinement fusion. That's when Los Alamos originally bought it, and I worked on it then. And here's a tour scene because here's the size of a normal-sized human being. So it's pretty impressive to see. It's a very, very large rotor for driving the pulses. We attract research from all over the world. In 2019, we had over 2,000 users from over 150 institutions all over the United States. And I like to, the director of the Magnet Lab likes to put up this and say, look, Delta hubs are Los Alamos, Gainesville, and Tallahassee, but this shows where people come in from all over the country and all over the world. We get people from about 300 institutions all over the world, including there's about a dozen magnet labs in the world, and we get people in from Sendai and Hefei and Wuhan and Nijmegen, and we all work together pretty well, and we're supportive. Newcomers are welcome. We have about 25% for PIs, our first-time Mag Lab users. And so all you have to do is fill out a form, and if it's publishable research, the user time is free. You have to get here. If there's a football game, you're welcome to stay with me. I have a big house. We publish a lot of papers, and we talk about that because the bang for the buck is very, very high. We really do enable a lot of equitable research around the country and around the world. We have several current records. I think besides showing a graph like this, I'll show a couple pictures here. So in 2017, we put into use a 36 Tesla series connected hybrid. You don't need to know what that means, except that it is so stable that you can actually do imaging in there. And so it's very, very highly overused. So you can do imaging at 36 Tesla. And I'll show you why you want to use these high fields for NMR and MRI. We have the highest all resistive magnets in the world. There's no superconductivity in here. One thing that I didn't have that slide. I forgot to put it in here. But we won, it was just announced in September that we won the R&D 100 award for our 32 Tesla all superconducting magnet. Why do you want? First of all, it's a really, as a user facility, no one can touch this. It's really fabulous. And why do you want all superconducting? Because the samples are already cold, number one, and number two, in the resistive magnets, you're rushing through about 550 psi of water to cool them. And as you know, you put a lot of current in a magnet, you get a lot of field. And if you're not rushing that water through, you can run this a lot quieter, and you have hope for scanning probes, which there was no hope for previously, and we're working on that. We also made a 45.5 Tesla all superconducting test coil. And one of the reasons why that was important is because NSF just commissioned us, they funded us to fund a new 40 Tesla superconducting magnet design. So we hope in several years to not just have a 32 Tesla user facility, but a 40 Tesla user facility. There's three major research themes of the Magnet Lab: materials, energy, and life. And I will give a couple of examples here. And so I'll just move forward, and I'll start with the materials examples. Everyone, so when I put this up here, I see graphene. I was just at a conference last weekend where everyone saw the JSWT mirrors, which are also hexagons. So this is a popular picture. So I want to just remind you what superconductivity is. Now, I'm a low temperature physicist, so I'm obliged, just like people in high energy physicists are obliged to have a picture of CERN. It doesn't mean anything, so I always have a picture of this. So in superconductivity, as you lower the temperature, the resistivity in most metals decreases, and then below a certain temperature, it drops abruptly to zero. And most of us understand this. It was a serendipitous discovery. It wasn't predicted at all. So this was conventional superconductivity. And it wasn't until 1957 that the mechanism for how the electrons are paired was discovered. So it was a very long time. That's conventional superconductivity. That's one of the few solved problems in correlated electrons. There are dozens and dozens of other solved problems. Just to give you a flavor for some of the other unconventional superconductors, what this graph is here is the vertical axis is the superconducting transition temperature, the temperature at which below the material is superconducting, and all superconductors to date need to be cooled. And the year that they were discovered, people, I don't know if this means much, but it's to show that whatever it has in red here is a conventional superconductor. We know exactly why it superconducts. Whatever is not in red here is an unconventional superconductor. So we don't really understand the mechanism for how the pairing works. And what I have put here is this picture that is ubiquitous. Where's my pointer? Come here. Okay, I can't. I'll just, if I can't point to it, I'll just, I'm stuck. Okay, that always, never mind. I'll use words. So in the lower right is a phase diagram. The y-axis is temperature, and the x-axis is a thermodynamic variable. It could be pressure, and it could be, oh, there's a pointer. No, it's there we go. It could be pressure, and it could be doping. And what is ubiquitous with all of the families of unconventional superconductors is that at very high temperature, at overdoping, at ambient pressure, at high pressure, you have what we call a Fermi liquid, which means we understand what the optical, transport, and thermodynamic properties are. So just to remind you, you can calculate all that. If you know what the atoms are in a lattice and where they sit, you can calculate those properties if you have a simple Fermi liquid. They're also called Landau Fermi liquids, etc. When you go underneath this, and if you go on the left side of this phase diagram, so that's ambient pressure, let's say, low doping, the material becomes a terrible metal to an insulator, and it's not insulating due to its lattice properties, it's due to electron-electron correlations. And it's in this region here that these funny little stars that I have here occurs. That's where you get these funny phases like electron pneumaticity, stripes. The electrons could get super, super heavy, like 1,000 times the electron free mass. And the actual reasons for why those happen aren't understood. Now, if you go to lower temperature, these two competing phases, they fight each other, and at very low temperature, what happens? In many, many cases, a superconductor forms. Wow. Okay, so what we have under here are going to be some kind of critical points here, and why exactly these superconductors form in these unconventional superconductors, what causes the Cooper pairing. Just to remind you, electrons are fermions, they don't want to fall into a single quantum state. So to make them fall in a single quantum state, they do this Cooper pairing mechanism. So they act like bosons, and it's more complex than boson condensation. But what causes them to pair in all these strange materials, like the high temperature superconductors, is not really understood. This, but I will say, I'm going to repeat this again. Up here is a conventional Fermi liquid, and down here is an unconventional superconductor. But all superconductors that we know of today are still Cooper paired. So just like we can use the Schrödinger equation and DFT or other electronic calculations to get the physical properties of the Fermi liquid, we can also calculate the physical properties of an unconventional superconductor. They're all Cooper paired. They may not be S-wave, they may have a different symmetry, they may be multiband, but you can use something called the Bogoliubov-Duhem equations, which are kind of like the Schrödinger equation, except there's two of them for electrons and holes, and there's a cross term, and you can do it. So, so what I have done, I started studying the superconducting properties, and I realized I wasn't learning much. So my own research is studying these strange electronic phases in these, which I call the unsolved non-Fermi liquid behavior or unsolved quantum materials. So I'm going to give you some examples from the Magnet Lab, and this was something that was just discovered a couple of years ago, well, 2019, so more than 2 years ago now. But the pandemic started in what, 16 years ago or something? Okay. These materials, I showed you one kind of complex phase diagram, and this is another complex phase diagram. This was discovered, this is a heavy fermion superconductor. By heavy fermion, we mean that the electrons, if you measure the electronic mass thermodynamically, is very heavy, and due to electron-electron correlations. Now, many of you know that below a certain temperature, as I mentioned, electrons are superconducting, and besides the superconducting transition temperature, if you put too much field, if you put too much magnetic field on it, you know, either electric field or magnetic field, current or field, you break the Cooper pairs and you force it to become normal. So that's critical field, and most people understand that. And what we have here is below a certain temperature at different angles here, the blue area is the superconducting area. And if you go up in magnetic field here, you break these white areas are where it's not superconducting. And it's just very strange. At one field, it superconducts all the way up to 35 Tesla, and then it becomes a field polarized magnet. That's interesting. And what's even more interesting is that at certain angles, if you go up to higher and higher field, you become normal, non-superconducting. And then above about 38 Tesla, it becomes superconducting again. Okay, no, we don't understand it. This is a very popular field. It's been studied a lot. And one of the reasons why they're interested in this is that this is what we call the Lazarus phase, because it lasts for so long. Might be something we call a triplet superconductor, which means the Cooper pairs are kind of polarized, and they're very robust, as you can imagine, at these high fields. And this may be a candidate for topological quantum computing or AI. Here's another example. Oh, by the way, I wanted to say these measurements were done at the DC facility in Tallahassee and also the Pulse facility out in Los Alamos. And here's something that's done in our electron magnetic resonance user facility. And this is just another example people like for AI. Without going into detail, you can send terahertz light into a magnetic material and send polarized spins into the magnetic material and carry information out. Now, the reason why this was interesting is because this happens faster than any other spin transport mechanism that's out there. So this is another candidate for high efficiency spintronic devices. This is still basic physics. These aren't in use yet. Nobody knows what, right now, cold atoms are still candidates for qubits. So we still need a lot of basic research to do. But in any case, we're working on this for high and efficiency spintronics devices. This is done at the EMR facility in Tallahassee. Now, I mentioned I have to say that we also work with CERN. So just like I had to show you a picture of the discovery of superconductivity, I have to show you a picture of CERN from the top. Not that it means anything, but it is really cool. And there's been a marriage of superconducting materials and high energy physics for decades and decades, all the way back to the 1960s, when niobium titanium wires were first used for bubble chambers. That's what CERN typically uses. Niobium titanium is a random alloy, so it's easy to make, and it's malleable, and it's reliable. And so that's the industry standard. When you go into a MRI, which is really cool because you get to go inside of a superconducting magnet, that's niobium titanium. Now, there are materials that have higher, they can take higher fields and higher currents, but they're harder to work with. One of those materials is something that many of you heard of. It's, where's the picture here? There we go, niobium 310. I'm having trouble with my pointer. So the magnet, I don't know why I'm having so much trouble with my pointer. The MagLab's research is, we've done work on a material called niobium 310. And that's harder to work with. It's more brittle. It's one of these materials that's not malleable. If you want to make a magnet out of it, you have to wind it and then burn it. So you wind the green material and then you fire it, and then it becomes a superconductor. Now, some of the discoveries that we've made have increased the HC2, the ability to hold field and current so much that it's now being wound from Fermilab, LBNL, and the Magnet Lab to CERN for the high luminosity upgrade. So just increasing that HC2 is going to increase the brightness for the high lumo upgrade by a factor of 10. We've invented a new material a couple of years ago that's hafnium doped niobium 310 that is being developed now that it might be used for the future circular collider. So anyhow, I like to show this picture because whenever I heard Fabiola Giannotti give a talk, she's always saying the limit of how strong we can, luminosity is limited by the magnet. So we're looking at the Magnet Lab, and it always makes me very happy that she quotes the Magnet Lab. So now I'm going to give you some energy examples. This is something that the physics community doesn't really know much about, and it's really great. And so I'm going to spend a couple of slides on this. And we have something called ion cyclotron resonance. And it's Fourier transform ion cyclotron resonance. Ion cyclotron resonance, or ICR. What it is a mass spectrometer on steroids. It was developed by chemists to understand the most complex fluid on the planet, which is petroleum. And what you do is you put in a spit of oil, and right now we can do, we have new detecting facilities that you put in a spit of oil at 21 Tesla, get the cyclotron resonance going, chirp it with a laser, and you get a mass spread like this. Now, the green curve is the time of flight with the primary competing technique, and you can see the high resolution of those spikes in the center that we can do. And why do you want to do that? So this is, nobody comes close to that. And let me also stress the mass, and this is my fake background here is the ICR detector. It actually has the resolution of about 1 electron mass. So why do you want to do that? I'm going to give you 3 examples, and I'll show a couple slides. One is the petroleumics. If BP and Exxon strike the same reserve, I shouldn't have well there, I should have oil reserve. It costs $1 billion to drill a well in the Gulf. They want to know if they hit the same oil reserve or not. And we can fingerprint it that good. We also do forensics. If there's an oil spill, we can tell exactly what oil head that came from. We have that kind of resolution. It's also used for proteinomics. For example, the p53 protein, as many of you know, the protein functionality is determined by its folding, and we can identify by doing deuterium hydrogen exchanges if the p53 registration, if the folding is going to be malignant or non-malignant, and all the way in between. And we can also determine protein makeups. And the other examples I want to give you, because they're very, very new, is climate change and sustainability. It turns out the second most complex fluid on the planet is dissolved organic carbon. So that's one of the things that we look at. We also study plastics and PFAS breakdown. So here's a couple of examples here. We look at the dissolved organic matter, dissolved organic carbon, samples around the Arctic to follow climate change. And this over on the right here is showing two kinds of runoff from asphalt, from the built planet. We can tell you if the runoff is island-shaped or archipelago-shaped organic carbon. And one of them is water-soluble and one isn't. And we're the only ones that can tell the difference because of our high mass resolution of about an electron. And so we can tell if we're going to be, polluting the planet or not. This is something that's very new that was studied that many of you know that plastic bags are bad for the environment. And one of the many reasons plastic bags are bad for the environment is they have these forever chemicals, which are PFAS, they call them, and they're very long photochemical, very long chains of carbon. And what turns out that was discovered by looking at Target bags and CVS bags and a lot of other kinds of plastic is that they are not forever chemicals. They're not completely inert. They break down into other long chain molecules. And we're trying to figure out, is this good or bad, more poisonous or less poisonous for the environment? So it's interesting to understand how we're polluting ourselves. I'm going on to life examples. These will all come from our Amherst facility at UF in Gainesville, Advanced Magnetic Resonance Imaging and Spectroscopy. So as I mentioned, when you go into a superconducting magnet, if you go into one, it's typically 2 to 4 Tesla. So that will give you about a millimeter resolution. And what you do in MRI is you line up the hydrogen, the water, right? MRI measures fluid when you go into a commercial MRI machine. And so one of the reasons you want to do it is to decide if you have a tumor or not, because tumors are thirsty and they tend to uptake the blood. So, but that resolution is about a millimeter. If you go to 21 Tesla, you can go to 10 micron resolution. So that's the increase in resolution. So now you can see subcellular structures. Now, I also, as many of you know, that when you're in an MRI machine, they're switching and putting on different kinds of fields, and you follow that with an RF frequency, and you're doing the spectroscopy using RF frequency. So one of the reasons why this resolution is so much higher at 21 Tesla is because you're using higher and higher frequency for the magnetic to RF frequency resonance condition. So if you're using, 10 or 20 times higher frequency, then you have 10 or 20 times higher resolution. But that also, you don't want someone to be in that MRI machine too long, because it's not as bad as a microwave oven, but you just don't want to stay there in a really long time. But one example where it's worth the risk is that at 21 Tesla, that's the earliest possible detection of plaque amyloids, which is agreed upon to be a problem for Alzheimer's, a reason why Alzheimer's forms. And the reason why this is useful, because the plaque amyloids that form in the brain actually cause microhemorrhages. So if you have that higher resolution, you can pick up with, in this case, 50 micron resolution, early microhemorrhages. So this will be applied later on in the health industry, because if you start getting other Parkinson's or Alzheimer's symptoms, it would be worth going in and to seeing if you should be taking medication for that if it's an early phase. So this is the earliest detection of plaque amyloids on the planet. Another example we have here is, why not unlock the periodic table? So now that we have this high this high field MRI, let's look at something besides hydrogen. We look at many different things. Here's, batteries, et cetera, et cetera. Here is an example, a life example of imaging sodium. So it turns out, I found out when I joined the magnet lab, you can buy a mouse with brain cancer and you can study its imaging at the sodium lines. So sodium is much heavier than hydrogen. So you're going to have the RF frequency is lower. You'll have a lower resolution, but you're specifically detecting the sodium. Why would you want to detect sodium? Well, when cells are dying, they uptake sodium. The actual mechanism isn't completely understood, but we know that happens. So this is what you do. You image the rat's brain on the left side in the sodium, and we see where the tumor is. You give the rat chemotherapy and measure it 4 days later. You can repeat that. And if that sodium lights up, like we see on the right here, that says that area has been uptaking sodium. The concentration of sodium is higher, indicating that those cells are probably dying. And that gives you some confidence that that is a good regime for chemotherapy. So this could be really life-changing for many, many people. So here's another example that is extremely recent, just within the last few months. So what you can do is take inside a living rat brain, you can put living stem cells that you can label with gadolinium nanoparticles, and you can track them in vivo, in the living mouse using MRI and see how the living stem cells respond to how the brain damage results from a stroke. And then you can see also in drug delivery where the stem cells are going and how the brain is progressing. So this is, I have 2 more slides for the magnet lab. This is one to say, if you want to be a user, go online. You can find what we have here, and we'll help you write the proposals. And if you haven't been here before, we'll help you out as much as you want. There's many, many experiments over all walks of life. And here's another example where we worked with a popular public engagement where we had a subatomic smackdown where we worked with CERN and had this big thing on the web about which is the strongest particle. Is it the electron or the proton or the, and so that was very fun. And we had, I think we had something like, over 2,000 views. And then I want to invite you all, and the last slide is that come to the Magnet Lab on February 25th. We have a big open house, and we typically have more than 10,000 visitors, and we can make it work. It's that big of a facility. Okay, so I already showed this, and I already stressed this. And so I'm going to go on here and talk more about superconductors and get to my analogy. So as I mentioned here, and I'll do this again, is that this is the phase diagram of a typical unconventional superconductor. Now, let me just tell you, it's typical. There's probably 50 phase diagrams like this, which I think they're all different families. But just like in quantum mechanics, there are some unconventional superconductors that look a little different than this, but that's okay. Just to remind you, on the right-hand side is a Fermi liquid. Underneath the dome is a superconductor, and above the dome are these unsolved quantum states of matter. And here are some examples. I just threw these up. The first one was discovered in the 60s. That's a heavy fermion superconductor. And what we have here is it's an antiferromagnetic state here, and the superconducting state is under this dome here. And this was the first indication that the old BCS theory of superconductivity wasn't going to work. One of the reasons is because what we find is that being next to a magnetic quantum critical point is good. So remember I told you magnetic fields kill superconductivity? In these unconventional superconductors, magnetism seems to be good. So there's a lot of magnetic pairing mechanisms, one I think that we discovered recently. So here's an example of a high temperature superconductor, superconductivity, Fermi liquid, weird phases here, organic conductors. There's things called dichalcogenides, the iron-based high-temperature superconductors, and a recent discovery is this twistor bilayer graphene also has this funny kind of phase diagram with the dome of the superconductor in the middle. And as I told you, I study what's over the dome. And one of the reasons I do is an intriguing point about the dome is that on the far right side, where you have a Fermi liquid, TC goes down. On the left side, we have highly correlated in a high temperature cuprate. It's called a Mott insulator. If you do the calculation, this should be a great conductor, but it insulates due to the electron-electron correlations. And then on the left side, TC also goes down. So too little, too much correlations are bad for superconductivity, but you don't get high TC without the correlations. So, to me, it's understanding that delicate balance between the correlated electron phase that are not superconducting and the superconducting phase. And so that's why I study that. And as I mentioned, there are some of the unsolved problems are, here we have the heavy electron phase. I mentioned the electron pneumaticity. These are data from my laboratory where we find, it's not as fancy as some people's, but where we find this electron pneumatic phase lasts up to like 175 degrees when superconductivity is like 30 degrees. So these are really, some of these are very high temperature correlated phases. And I mentioned stripes and pseudo gaps. There's dozens more. So, so this is where I start getting really general and broad, and I'll go to my analogy, and hopefully I'll be done very soon. How much time do I have? 2 minutes?
We're in the time of the questions, but you can use still, I don't know.
Okay, so I'll just go on to the, I guess what I want to say is that there are many kinds of unsolved quantum matter. And what we've done in condensed matter physics is developed many, many new ways of measuring it. There are all kinds of new techniques that are fascinating. This on the right here is called quantum oscillations we do at the Magnet Lab. There's STM, there's ARPAS, et cetera, et cetera. The other thing that some of my new measurements were possible because the crystal growers have just done amazing things and things that we could never measure before. We have amazing crystals, and computation has progressed a lot. So I want to point out here, let's just go on to conventional superconductors. As I mentioned before, above TC, you have a Fermi liquid. Below TC, you have Cooper pairs, and we know how they're formed, and that those are solved problems. In unconventional superconductors, on the upper right side, we have simple metals. Underneath the dome, we have Cooper pairs. We may not know how they're paired, but we know they're Cooper pairs. And above TC, we have this weird unsolved quantum matter. And so the many phases of quantum matter remain unsolved. So moving on to the analogy. Okay, I went to Kip Thorne giving a talk at a Cavity Lover 2016, and I came up and they won the Nobel Prize with Ray Weiss, Barry Barish, and Kip Thorne for the LIGO experiment, which was really cool. And this picture here reminded me a little bit of the BCS theory. So let me just move on. What I think I'll just go on to here. I'll start with this. What I want to stress, the take-home message here is that the gravity wave detector, LIGO, was the best $1 billion NSF ever spent. It measured two black holes colliding, and they knew what they were looking for. The energy was more powerful than all the combined power of all light of the stars in the universe. And they measured a distortion in the interferometer that was less than the width of a proton. They knew they were going to find the gravity wave. The important thing about this is this, for the first time, we have a way to look at the universe beyond light and matter using gravity waves. And my analogy is looking at in the quantum matter is we have many new detectors, the increased crystal growth, the many measurements, and the computation techniques. So here's where I beat up my analogy. Mr. Newton figured out that 1 over M1, M2 over R squared worked. And Mr. Einstein said, this isn't quite working. And he looked at the retrogradation of the perihelion of Mercury, et cetera. And his explanation was this distortion of the space-time continuum. Mr. Fermi had this explanation. Bardeen, Cooper, and Schrieffer found one place where it didn't work and solved one of the dozens and dozens of quantum matter questions. So we still have many questions that are unsolved. And here's the really beating up the analogy, which is In gravity, the forces between objects are derived from the mass and the position of the objects in the universe. And the properties of the simple metals are derived from the crystal atoms and their positions. The Einstein general relativity theory is that this theory, the attraction, is the distortion of the space-time continuum. The one solved problem, some of you already know, it's the distortions in the phonon spectrum, in the lattice, that cause the electrons to pair up. So there's those kind of distortions, and we're hoping they help us solve the unsolved problem. That's a publication that we think it's the F-level pairing in a heavy fermion superconductor that causes the Cooper pairs. And here's my conclusions. My take-home thing is that I hope you had fun, and that there are just many, many unsolved problems in quantum materials. They're intriguing, and I think understanding each one separately will have a tremendous knowledge in our understanding of the universe and for quantum computing. And that's it. So
thank you very much, Laura, for this very impressive overview and also this analogy. It's a very interesting way of looking at the different problems in different fields. Very nice. And now the talk is open for discussion. So Laura has a question. So Laura, can you? So Laura Sagunsky, not Laura Greene.
Some confusion here. Yeah, thank you so much for this really impressive overview. What you do, I was really excited. I want to ask again. You talked about cancer therapy, and you mentioned that basically that when the cells have sodium, that this is an indication that they die. Did I get this correctly? That the sodium is an indication, or is it that the sodium makes them die?
So that's a very good question, and we don't really know the answer to that. But we do know that when cells are dying, okay, they uptake sodium. So if your chemotherapy is successful, that tumor will uptake sodium. And also in aging, when cells are dying, they uptake. It has to do with the sodium pump, But the actual so all this detects is increased sodium, which means that tumor is uptaking sodium, which is an indication that it's probably dying.
Right. Okay.
So if that makes sense.
Yeah. Okay. Very interesting. Thank you.
So on this relation, you are talking about this 21 Tesla that you can use then to have a high resolution to see any living tissue. Now, you were also mentioning about how it can be dangerous, right? For if you are too long exposed. So is there any hospital that is already using these techniques?
No, it's not any. It's still, these are still rats. You can go to higher Tesla. I think 7 Tesla is the highest commercial MRI. I might be wrong about that, but I did look that up recently. And that's not dangerous. And it's not very dangerous. Again, it's not like going into a microwave, but you just don't want to be there for a very long time. And right now, MRIs, they switched the name from NMR imaging to MRI because there's nothing dangerous about it. People were afraid of nuclear magnetic resonance, and there's nothing dangerous in there. And if you go into a hospital, except for it's a drag, and you want to go to higher fields because it takes less time. Right, you can get higher resolution.
Because they make you stay for a long time inside these. So that's.
But if you go to a more modern hospital, they'll have higher fields and higher resolution, and it can be a long time. It's boring, but it's an amazing technique, right? I mean, if you can actually figure out so much imaging, and like I said, for tumors, it's still. Biopsies are still the best way to find things, but you can see if there's a pooling of blood. So now certain kinds of people who have had breast cancer, et cetera, they recommend MRI over mammograms. I get an MRI and a mammogram once a year, every other year, because my breast cancer wasn't detected by X-rays, it was detected by MRI. And so it's very interesting that we have these techniques.
Yeah, indeed.
So there's nothing to be ashamed of. I think everybody gets prostate and breast cancer. It's really common.
Yeah. So we have a question from Falco.
Yeah, thanks very much. I was interested in since you're you take pride in having the highest magnetic field. I was wondering what's the what's the prospect of going to even higher fields than the ones you have now, or is there some natural, some upper limits that you could go to, or is?
Thank you for asking that question. We discuss that all the time. Right now, so for instance, our 101 Tesla pulse magnet, the reason why it's so reliable is because of this generator and what we do. And the reason our 45 Tesla magnet is so reliable is because we are constantly doing quench runs. So it's very reliable. There are many people that make, there's other people that have made a 20 Tesla, 30 Tesla superconducting magnets, and they become great doorstops. So we're very, very good at the diagnostics. One of the limiting factors isn't the superconducting material or the copper in the windings. It's to keep the magnet from exploding, right? You have these Lorentz forces that want to tear it apart. So a lot of our research is just in stability of the magnet itself. And I showed you the little test coil that was 45T, right? Just a little baby test coil, but that showed the feasibility of making a 40 Tesla all superconducting magnet. We do have plans for a 65 Tesla DC magnet, and that would be very exciting. I will also say that one could also make a pulse field. The Russians have done this, and we've done this in Los Alamos, about a 250 Tesla pulse magnet, but it's not really that useful. It's a single turn copper, and you put your sample here and you explode it in the desert. And if you get to, and sometimes you can get, and actually in the early days of high TC, that's how they started measuring, because the HC2 of high temperature superconductors is so high that they used to do that for high temperature superconductors. I will also say that you asked about the magnets. Right now, the very highest magnets are using cuprate high temperature superconductors. Not because the TC is so high, because you take them to low temperature and it can sustain a higher current and a higher field than any other material on the planet. So that's why you need high temperature superconductors and high field magnets.
So perhaps discovering new high temperature superconductors will feed back and help your facility.
Yeah, we just started a program on that. We just got funded in something called ExcelNet for the National Science Foundation with something called ICANN. And man, I've been involved in looking predictive design of new superconductors for decades. And still the best way to find a superconductor is serendipity. Okay. And I can give you examples why that's true. But yes, I really believe with all of our new tools, we'll get there. We at high fields, you can really get to what we call the quantum limit, what's going on in this material. And, I believe that these studies will help us get to predictive design, but man, it's very fundamental, very complicated stuff.
Okay, thanks.
So Laura, now I have a question. Maybe in the US, you are not as much affected, but in Europe, as you know, it's the question of energy is it's really now a big issue, and CERN has PSI and all these big labs. They have to now consider about how they what happens with the amount of energy that they need. Now, I guess that all these high field magnets, you need lots and lots and lots of energy. So is it an issue right now in the US to run these labs, or you also have to do some kind of rescaling?
No, it is an issue. And I wish I had the numbers on the top of my head. You could look it up. It's like $1 million a year in electrical costs in Tallahassee. And they used to say at the old MIT Magnet Lab that all the lights would dim in Boston. But we have ways to do that. We have our own cooling towers, et cetera, et cetera. Mm-hmm. And we work with the city of Tallahassee and Leon County. And in fact, when you use magnet time in the DC facility, it's not by hour, it's by energy you use. So, how many kilowatt hours are you using in your magnet stay? It's a problem. And that's also an argument that why you want to use superconducting magnets, right? Because once you cool them down, you can get in persistent mode and it takes less energy to run it. These high field magnets, if you didn't have these high field hybrid magnets or DC magnets, if you didn't have that 500 PSI of water running through, they'd melt immediately. So yeah, it's a problem. And MRI magnets now, they run in persistent mode, and you just have to give them a little drink of helium now and then. But yeah, it's a problem. But like I said, that $1 billion that the U.S. spent on LIGO is just,
indeed,
it costs money. It costs money to do research.
Yeah,
and it's just, and look at the gains that we've had. Some guy wanting to know how, I think it was Rabbi wanting to know how nuclei move in a field gave us MRI, and the standard one, GPS from general theory. We all have these things. So
I agree.
Very, very important. And I also want to say, because I do a lot of advocating for science, that if you look at developed countries, GDP and funding that's put into applied and fundamental research track.
Indeed.
And so you could really argue economic reasons why you want to fund. And then I gave a quote at the PCAST meeting yesterday, was that when R.R. Wilson was testifying in the 60s, I think it was, to build Fermilab to Congress, and you've probably heard this before, a congressperson asked him, will this help our national security? And Wilson's answer was, it will not directly affect our national defense. It will just make the United States worth defending. So that's
a good answer. No, I didn't know.
It's a great quote.
That's really a good answer. Yeah. Okay, so I think that we are reaching the end of our conference. It has been 3 days of very interesting talks, interesting discussions. Thanks, Laura, also for yesterday for being in this panel. So it has been really nice to conclude with you. And now I pass the screen to Laura. So Laura, now is your turn.
Yeah, I want to keep it short. I first of all want to thank you, Laura, and all the plenary speakers again for joining this conference, for giving such amazing talks. We just had this feedback session, and one remark that I got, what was amazing, is to see so many inspiring women, really the variety of physics in all its different fields. So I want to thank the plenary speakers. I want to thank all the participants that are watching us here and also on YouTube. And I want to thank finally, last but not least, my amazing colleagues from Goethe-Universität who supported this idea, who helped to make this happen. And it was really an awesome experience. I also want to thank my research group, and one person from my research group particularly, namely Tamara, who has done a great job and has helped so much with making this conference happen. So thanks to you all, and this will be, or hopefully not, the last edition of Wow Physics. We have support from the International Association of Physics Students already for the next edition. So no date and time fixed yet, but at some point in the near future, hopefully there will be a second edition. So thank you very much.
Thank you. Thank you.
It was fantastic. Thank you.
Thank you. Bye-bye.
Bye.
Bye-bye.
See you at the next edition.
Yeah.